Never before in the history of aviation have the scientific genius and the national resources of two peoples been so focused on one commanding and common project as they have been on Concord.
Machines and men. Human brains and electronic brains working together so that airline passengers of the 1970s can fly in confidence and in comfort far above the earth and at twice the speed of sound. Daily, in this quiet room and in many others like it, the Concord computers give the machines answers to man's most urgent questioning: aerodynamics, structures, performance. The compound of the highest state of the art, yet harnessed to our common use.
In the beginning of this project were many theoretical aerodynamic forms for a supersonic airliner. Hundreds were studied and rejected before the now familiar basic shape of Concord was determined. This aerodynamic research program, one of the biggest ever staged, used more than 50 different wind tunnels in Britain and France. Concord's aerodynamic problems have to cover the widest speed ranges. Low-speed problems are investigated in subsonic tunnels, like this one at BAC Filton. Many wind tunnel studies, this one is at the Établissement Aéronautique de Toulouse, EAT, have been made into the aerodynamic effect of kinetic heating, the heating caused by the friction of air passing at supersonic speed over the aircraft surfaces.
A new aerodynamic problem for civil airliners. Shockwaves. A Schlieren film records the shockwave formation at supersonic speeds. One of the many supersonic tunnels used on the project, a Mach 2 tunnel at EAT. In any supersonic aircraft, the aerodynamic efficiency of the engine air intakes is of supreme importance. Airflow to the engine must be precisely matched to its widely varying requirements in different phases of flight. Wind tunnel model tests are used to check refinements in the design of Concord's variable geometry intakes. A great deal of the development work on the Concord intakes has been done in BAC's high-speed wind tunnels at Warton, Lancashire, one of the finest supersonic test facilities in Europe.
5, 4, 3, 2, 1, start. 5, 10, 15.
In a typical test run lasting only a few seconds, some million different data points are recorded and plotted.
5, 6, 7.
All this information is fed by Warton directly to the Filton Computer Center for rapid processing and analysis. Another kind of tunnel, using water instead of air. This is the hydrodynamic tunnel operated by ONERA, the French National Aviation Research Authority. Colored inks injected into the water stream trace the airflow patterns over the Concorde wing at low speed. Rear view of the model in the same tunnel. As Concorde comes into land, These stable vortex formations will provide valuable and natural additional lift.
Like Concord aerodynamics, Concord materials have had years of testing. In French and British laboratories, thousands of samples have been tried out. Here are a few of them, tested to destruction and filed for reference. Many different kinds of material, aluminium alloys, titanium alloys, stainless steels, were examined. At the Royal Aircraft Establishment, Farnborough, an electron microscope is used to probe into the very elements of complex metals. Only after innumerable checks and tests was the final choice made for Concord's main structural material, a metal used in aviation for the last 40 years, aluminium. This aluminium alloy, known as RR58 in Britain, AU2GN in France. Special laboratories like this one at Farnborough have devoted thousands of hours to establishing the creep resistance of RR58. Creep is the slow deformation of metal that can be caused by prolonged loading combined with prolonged heat. From these tests, this alloy has emerged triumphantly.
Kinetic heating imposes new demands on aircraft materials. Everything for Concorde is with heat added. So electrical furnaces are wrapped around test specimens to simulate the structural heating conditions experienced in supersonic flight. Stringent testing has demonstrated that in this new flight environment, RR58 has excellent fatigue life characteristics.
Like all Concorde activities, materials testing in Britain and France is dovetailed into a single coordinated program. Investigations in this Farnborough laboratory form one strand in a complex pattern of research.
Another strand, the Vibraphore room at EAT Toulouse, where the spotlight is turned on the fatigue effects of structural vibration.
It is not only the basic materials that have been put to the test. Sealants, adhesives, protective finishes, all these have been studied as thoroughly as the metal itself. Here, a bonded joint is being heat tested. And here are the results on some of the many different glues that have been put to the test.
From materials research onto structures research, structural testing in miniature. This instrumented model is used to establish the characteristic vibration modes in the airframe structure. One of the structural problems is acoustic fatigue. High-intensity sound waves generated by Concorde's 4 Olympus engines could induce fatigue in the adjoining airframe structure. To make sure this doesn't happen, Concorde test specimens are bombarded with noise unlimited. To drive the sirens of the Sud Aviation Toulouse facility requires vast quantities of compressed air. This is just one example of the scale and complexity of new facilities needed and supplied to solve Concorde problems. more structural research. And again, the subject is kinetic heating. Its effects on various parts of the Concord structure are reproduced and studied in special test rigs. At its cruise speed of 1,450 miles per hour, air friction raises Concord's surface temperature to an average 120 degrees centigrade. Very rapid changes in skin temperatures occur while the aircraft is accelerating or decelerating from supersonic speed. And these changes set up thermal stresses in the internal structure. This problem has been overcome by careful design backed by painstaking research. This test program covers the whole structure and will lead up finally to the testing of complete airframes. This rig at BAC Filton uses a new technique in kinetic heating tests and is the forerunner of much larger installations. A 15-foot-long fuselage specimen is being subjected to heating, cooling and mechanical loading cycles in a kind of giant wind tunnel, where the thermal cycle is reproduced by blasts of hot and cold gas. Nitrogen is the cooling agent.
Comprehensive ground testing, years ahead of the flight program, protects the structural integrity of the Concorde. All Concorde structural testing is aimed at ensuring an airframe life of 45,000 hours, equal to 12 to 15 years of intensive airline operation. From structures onto the next stage, proving the aircraft systems. At RAE Farnborough, the cabin air conditioning system had its preliminary testing. Tests proved that Concorde passengers will be very comfortable temperature-wise. This half-section fuselage specimen is used at Sud Aviation's Blagnac laboratories for tests on cabin cooling and insulation. More extensive air conditioning research will be done in this high-altitude chamber at EAT Toulouse.
Another major new Concorde test facility, the Fuel Systems Laboratory at Filton. On the Concorde, fuel is used for aircraft trimming, and this rig will check functioning in all flight attitudes. The Electrical Test Laboratory at EAT. Although the development of the Concorde's electrical system is primarily a British responsibility, some of the equipment testing is being done in France. To supply power for the flying control system rig, a French responsibility, standard aircraft alternators are being used. Functioning of the electrical system will be exhaustively tested on this full-scale rig at BAC Filton. Not only overall systems, but individual system components must be ruthlessly checked. A hydraulic system is as strong as its weakest pipe. This EAT rig is designed for testing fuel pipes. In the supersonic flight environment, there are new heat hazards which have to be provided for. Here the search is on for toughness, strength, flexibility. In short, for absolute safety in fuel supply.
In the Concorde, many standard aircraft components are being used, but some have had to be designed to operate at new, higher levels of reliability and efficiency. Even seals will have to be better than ever before. This EAT rig and the men in charge of it will make sure they are. Full-scale wooden mock-ups, like this wing at Sud Aviation Toulouse, provide answers to a different kind of Concorde problem. The down-to-earth problems of installing all the 1001 things like the undercarriage, the miles of electrical wiring, the pumps, and all the other equipment that has to go into the aircraft. Time and money are saved at the production stage by using three-dimensional design aids like this to study complicated installation problems and to solve them in advance. There is a mock-up for every part of the aircraft. This is the engine variable air intake.
And this is the power plant mock-up, with the dummy engine being winched into position. During development, this job will be done hundreds of times to check that relocating any accessory has not affected engine installation or interfered with its servicing and maintenance. With this mock-up at BAC Filton, designers plan flight deck systems and all the network of underfloor trunking, ducting, wiring. In the flight deck mock-up at Filton, alternative layouts can be tried out.
Flight research in the same field is being done by the BAC 221. This aircraft has a slender delta planform similar to Concorde's. It's being used by the Royal Aircraft Establishment for the study of slender delta aerodynamics and handling at subsonic, transonic and supersonic speeds. For years past, another British research aircraft, the HP 115, has been demonstrating the superlative low-speed handling qualities of the slender delta.
Other Concorde problems have been tackled at the Honora headquarters near Paris. Wind tunnel experiments here have helped to develop the complex variable geometry exhaust nozzles of the Concorde's Olympus engines. These nozzles, like the intakes, contribute largely to the overall efficiency of the engine. These are actual nozzles on test. Snecma, the French engine firm that is collaborating with Bristol Siddeley on the development of the Olympus 593 engines, is responsible for the rear end of the engine, including the exhaust nozzles.
The problems of Concorde power are being solved. At the Bristol Siddeley test facility, basic Olympus engines have already run for long periods. Once again, engine testing is a coordinated Anglo-French activity, and the work here is complemented by the Olympus testing being done by Snecma. These are representative flight type 593 engines.
And this is a representative airframe section for flight deck air conditioning and bird impact tests. A fuselage section to be built into a large structural test specimen. A Concorde air intake made in stainless steel and aluminium for ground testing. In this new Farnborough laboratory, opened by Her Majesty the Queen in June 1966, a complete Concorde airframe will be fatigue tested in supersonic heat conditions. In this similar laboratory at EAT Toulouse, another Concorde will be static tested, again with heat added.
But first, structural tests will be made on a large test section like this, section 2.8, built by Sud Aviation at Blagnac, Toulouse. Or this, section 2.6, another Blagnac piece.
And here, section 2.8, completed and ready for the new Toulouse Structures Laboratory. Here at EAT Toulouse and Farnborough, major specimens under test will each have its own research program concentrating on the structural loading test most critical for that particular section of the airframe. But sectional tests, important as they are not good enough. Concorde's designers are convinced that structural tests on complete airframes are the essential final proof of integrity. Section 2.6 is ready for the laboratory and to take its place in the vast test program.
Machines and men, linked in the most thorough development program ever known in aviation. Behind the development program has been research on a new scale, and supporting both are the full material resources, the tremendous equipment, and the combined scientific and engineering determination of two nations to whom, in its short history, aviation owes so much of its original thoughts. By the time Concorde enters public service in 1971, it will do so from the greatest research and test program ever yet mounted in support of an aeroplane.